Hi, my name is Turgay Gokar. I am Director of Advanced Development LTO for Quantum Corporation. I've been with LTO for many years, since first generation. Now, that's a lot of years. When I first joined LTO, I was a young engineer or younger engineer and trying to figure out what tape drives are and how can I contribute to a 100 gigabyte tape drive project, which I had no idea where it was going to end up being at. All these years later, I'm here sharing you information, technology about 18 terabyte LTO-9, and also presenting some of the potential roadmap options where we can go beyond 100 terabytes tape drive products. Let's see how it happens. LTO-9 technology and two-dimensional erasure-coded long-term archival storage with Rail architecture, where Rail stands for Redundant Array of Independent Libraries, which we all are familiar with. Is tape dead? Many have said that over the years, but tape is not dead. Actually, it found a new place as a tier storage system in data centers, all the hyperscalers. So when we basically look at this slide, we see two pictures, one on the upper right corner and the one on the lower. The upper right corner is the standard INSIC technology roadmap showing hard disk drive and tape technologies. And the lower left-hand corner is the LTO tape and INSIC technology and product roadmap. Basically, LTO has successfully followed INSIC areal density roadmap with 22% per year growth rates compared to 7.6% per year by hard disk drives over this last decade. One of the key points to make is the fact that tape areal density demos played a key role in LTO technology. For example, 2.6 gigabit per square inch demo back in 2007 eventually found a home at LTO-8 product with 8.5 gigabit per square inches about 10 years later. And it's also important to note here that there's some key comparisons between hard disk drives and LTO as it's written on this right-hand section of the slide. If we take 18 terabyte hard disk drive, and which requires 1022 gigabit per square inch areal densities, and compare it to an 18 terabyte, same capacity LTO-9, which only requires 12 gigabit per square inch density, we find out that LTO has a huge advantage over tape in terms of volumetric densities. I mean, you also need to consider, besides the fact that tape has substantially more recordable area, like more than a kilometer long, half-inch wide tape that we only use today, the one side of the media. Also, this is packed into about 60% of the volume of LTO-9 of hard disk drive. So LTO-9 cartridge is substantially compact, volumetrically efficient storage medium when it's compared to hard disk drives of equal size capacity. If you add this thing to the green operation and low cost, and the fact that it has an air gap for ransomware operations, it's not surprising that LTO has really finally found a home at hyperscale data centers. This slide talks about what we predicted back in 2012 with INSIC roadmap and what LTO-9 technologies is able to achieve nowadays. And basically, what we're showing here is the fact that back in 2012, INSIC conducted a very comprehensive roadmap. It included technologists from all over the world with different companies, including IBM, HP, Oracle, Quantum, and also Fuji, Sony, various substrate companies, particle companies, plus the universities. And we developed what we would predict 10 to 15 years down the road, what the tape would look like. So when we start analyzing this thing, the one on the right-hand side showed what we, the technologists and universities, predicted tape bit aspect ratio, BAR, would look like in about 10 years down the road. We predict eventually 2020 type timeframe, the BAR would reach from about 80 to 100, which was back then, down to 25. And today, if we look at LTO-9 BAR values, it's around 25. So we predicted below 33, and we actually achieved 25. Now, how did we do that? Is with higher track densities at 21.897 kilo tracks per inch, and higher areal densities at 12 gigabit per square inch. When you add this thing to the longer tape, TMR technologies, and the new ECC formats that allows us to reach about better error rates than one error event in 10 to the 20 user bits, it shows the capability of what we were able to achieve as a technology and what we predicted back about 10 years ago. Now, there's a couple other things in here is worth mentioning, and basically that is TDS control. Back those days, we said we need to substantially improve substrate, which would have cost more higher costs, and then increase data bands. Also would have add complexity and a cost. What we were able to do with LTO-9 is use optimized media, new ECC format, and new drive algorithms for very precision shingling. Combine all these things with areal densities, we're able to achieve 18 terabyte capacities with extremely high durable data recording archival system. This slide talks about a different view of areal density, and this is basically shows how we can achieve a true comparison of the core technologies between tape and hard disk drives. The previous areal density plot shows the areal densities on the y-axis, year in the x-axis, where AD is in logarithmic scale. Here, we transpose that one into a three-dimensional picture where x-axis is track pitch in logarithmic scale, y-axis bit size in nanometers in logarithmic scale again, where the areal densities are shown as contour lines, red lines, going from 15 all the way to 15 gigabit per square inch, all the way to 10 terabit per square inch. You can easily see that tape is still located in the upper right-hand corner around 15 gigabit per square inch areal density contour line, where today's hard disk drives with green square data points are shown to be scattered around 1 terabit per square inch areal density contour lines, where their track pitches are less than 100 nanometers and bit lengths are around 20 nanometers. So eventually, this has to go all the way to 10 terabit per square inch, which has to put them into an area of sub 10 nanometer bit size. And there is a huge challenge doing this at cost and at scale using rotating mechanical devices and being able to control bit dimensions to these very, very, very small sizes. Whereas tape's challenge is going to be going to from 15 to 100 or 200 gigabit per square inch. Now, both Western Digital and IBM recently did technology demos that says magnetically this is very possible, which leaves the only challenging technologies to resolve to reach these very high areal densities compared to where we are with LTO-9 is the dimensional stability and track trimming, which we'll go over that in detail next slides. Dimensional stability, TDS, can be, tape dimensional stability, or some say transverse dimensional stability. The definition here is taken from INSIC 2012 publication. It's in the web, and basically says over environment and age, the width of the tape expands and shrinks. And when that happens, you need to control and manage and have countermeasures to deal with it. Now, back in 2012, we discussed that, and earlier we discussed that for many years, and a lot of research, a lot of patents, a lot of work and publications has been done on this technology area challenge with flexible media, which is a polymer type substrate. And I'm listing some of them here, like tension control, ECC, reduce head span, azimuth control, shearing head piezo, stretching head by other means such as heating the head structure or something like that, and readers with narrow and different sizes, narrower readers at the edge, wider readers in the middle, and different substrate, different servo bands, and maybe the holy grail is adjacent write technology. Now, Just Quantum has many patents in this area dating back to STLT days. So this is an area, it's not something new. All the tape companies, media companies in universities have researched this extensively. Technologies, things are known. Implementation is what is based on what the need is. Illustration of dimensional stability. This is just to give you a picture what this problem may look like. It's a crowded one. I'll try to walk you through it. The chevron patterns on the top and the bottom are servo. Green bar is your head. The left-hand side picture, we're basically showing tape drive and media operating, writing and reading at high temp, high humidity condition. Tape is stretched, tracks are written and trimmed. And when it's read, it reads perfectly. Everything is in place. Now, in here, just to point out a couple of things is track N is written, and then track N+2, which is the next forward wrap, is trimming track N with shingling. And then what the reader has to do to read the data later on is read the trimmed or shingle section of track N, which is the actual track width prescribed by the format. And if everything is, fits together, the environmental conditions during writing and reading, you're perfectly aligned. Now, 6 months later, you want to read this tape at a cold and dry condition. Tape shrinks. Now, as the picture shows here, you try to put the servo readers on the chevron. You're going to balance this thing to compensate for the dimensional stability. That's one of our features of LTO technology. And then try to read the data. But however, if the changes is too much and you don't have the compensation techniques, then your top reader and bottom reader will be off track. Top reader will be above track N, bottom reader will be below track N, channel number 32 or 31, if you count from 0. As a result, you will lose 2 channels worth of data in this thing that if your ECC is strong enough, you can recover. Otherwise, you have to do retries. This is dimensional stability. LTO-9 numbers. Put this one here. These are it's kind of critical numbers, compares the LTO-8 and change. Capacity, key numbers, I'll go over this thing. Nominal capacity, 12 terabyte versus 18 terabyte versus 12. There's a 50% increase. Transfer rate, we have 33% increase, 300 to 400 megabyte per second. Areal density, key technology, is 8.5 to 12. It's about a 40% increase. Tape thickness is reduced. It's now thinner media. Why? Because first time in the history of LTO, we actually use more than a kilometer long tape. This is a massive achievement, all in the same cartridge space. And we got more wraps, 280, which means times 32. You get more tracks. That's 8,960 tracks. That's 35% increase over LTO-8. And important thing to note, our track density, TPI, first time, again, in the history of LTO, we have gone above 20,000 tracks per inch track densities. This is massive. We have broken through a big technological ceiling here. And one of the key things of LTO, I'll go over that next slides, is the user bit error rate. Now, we have a new C2 code. Same efficiency as current C2, LTO-8, what with more parities, double the parities, which makes our system, LTO-9, far more reliable. And this is based on quantum's ECC modeling and channel study. And we it's a mathematical study based on what we know, what we have measured, what we have experienced over the years. And then we can confidently say that the error rates, UBER numbers, based on quantum methods, is around one error event better than 10 to the 20 user bits. And compared to 10 to the 19 user bits for LTO-8, that is 10x improvement compared to LTO-8, all because of ECC, new format ECC. Next slide, we'll go over this format a little bit more deeper. Basically, user data is now a bigger chunk. Why? Because we have a new long code word, C2. That increases the data set size for LTO-9 from 5.031 megabyte size to 9.8 megabyte size. So that's like nearly doubles the size of a data set. However, C1, C2, metadata, all interleave, all calculated and spread across down the tape and across 32 channels. So with this new C2 ECC, this is why you're able to get 10x better UBER numbers compared to LTO-8 per quantum's modeling. And also off-track events we're robust compared to LTO-8. In LTO-8, you had half the parity, so basically now you can be more off-track, longer off-track, and be able to recover data. Is better, more robust tracking performance. Overall, it's a very highly durable, highly efficient system. Because it has doubled the parities, there is an ECC play here for the dimensional stability. In some cases, if you lose top and bottom edge of the tracks due to SNR loss, due to off-track conditions, due to dimensional stability, some corner cases, you can still recover with remaining ECCs. Why? You lose half the ECC, so you go from 24 parities down to 12, which is where LTO is without losing any parities. So LTO-9 is extremely robust, extremely durable system, has various countermeasures for dimensional stability and data durability with higher UBER numbers. Some of the new features, there's a couple of new features, and one of them is capacity efficient partition format. In typical LTO, when we use multi-partition tape, we use guard wraps to isolate the partition. So when you write one partition, you don't overwrite the other partition due to shingling. That resulted in loss of capacity to a few percentage. What we have done in LTO-9 is introduce a new capacity efficient format for special cases of 2 and 4 partitions where each partition equals size. We now, based on a format, we use servo bands as guards. Therefore, we don't need extra guard wraps costing us capacity when we employ this type of a partition format. Perfect application for object store, where you have big chunks of objects for partition tape. Each partition will have now 4.5 terabytes without losing any capacity, the guard wraps, and you can write and read and rewrite any partition without worrying about overwriting the whole tape. So it's an excellent opportunity for object store type applications. There are 2 other features. One is archival storage, which is basically the thin media, 7% thinner, and longer media, more than 1 kilometer long. When it's placed to store for long-term durability, like 10 years plus type of applications where most tapes are all used at, yes, some may migrate them after 7 years, but you want to keep these things for many, many years. And you basically end up, you need to, with the media thinner, you need to make sure your packing stresses are controlled. Drive has optimized algorithms built into it, which basically when you do an unload command, it moves the tape based on your loss operation to the EOT, packs it with precision mode of tape motion and packing control, which gets the media ready for offloading and storing for long-term storage type case. And that may increase your unload times up to 4 minutes. The other one is the cartridge optimization. This is done one time in the life of the media. This is important because we need to be able to trim and shingle and write data with this flexible media over temperature, environmental ranges, precision, such that we provide the 12 nines durability as, claimed durability with this type of application, where if your errors are random, you can actually, estimate your durability to be such based on these BER numbers. And that is a one-time application, and it really is done at the very first load of any media. And it takes about 40 minutes, definitely less than 60, but, some cases may take up to 2 hours. But nevertheless, if you look at the overall picture, life of a data on the media, more than 10 years, this is less than something like 0.001% of the overall life of the media. So from a grand scheme of things, it's a very small amount of time. Yes, it does add a latency to the beginning of the system for each tape that is brand new, that is used. Any drive can do it. Any other drive can utilize this metadata. So it's a very innovative new algorithm that adds to the durability of the LTO-9. One of the very interesting features is the RAO algorithm, aka Quantum calls this reordered read. It basically, you send a batch of files, excellent for object store. If you send a batch of files to the drive will look at the logical order, and then I find out where those files are located on tape, wrap number, and LPOS location from beginning to end, physical location, and reshuffle those guys, order them based on an algorithm such as traveling salesman problem, and then gives you an ordered list. Now you use the order list to be able to read your data. You get benefit, less time, less meters of tape motion, both win-win situations. Here's an example. We just did a test in Quantum Labs. We took a bunch of files, 2 gigabytes each, and we read them in order and without order. Without order, standard legacy method you use, it takes 18 minutes, but we did it in 11 minutes. So we definitely saved time, 7 minutes out of 18 minutes. And then without order, the tape motion was 8,201 meters. Our approach with RAO algorithm provided by the drive, it's only 5,328. Less tape motion, more durability, better wear and characteristics with the media. So overall, it's a great tool, great feature to have. The other last one is the environmental requirements. The only change here is basically between LTO-8 and 9 is the wet bulb temperature 26 degrees has been replaced by 22-degree dew point temperature. Only affects the allowable range. Recommended range for years with LTO-1 through 9 has never changed. That's the green zone. Now we talk about two-dimensional erasure codes and locally repairable erasure codes. Erasure codes with tape have long been researched dating back to early 2000. RAID-based systems have been developed using parity tapes where erasure-coded data chunks are striped across multiple tapes. However, unlike erasure-coded HDD object store, restoring files with different sizes will require multiple tapes to be loaded, which may cause long tail latencies because of high cartridge to drive ratios, typically with our application, with libraries. Two-dimensional erasure-coded technology is based on existing and pending quantum IPs, and basically it's used to address the key issue, which is long tail latency problem. It offers users to read files and objects using single tape or multiple tapes. It's an option. If you want faster transfer rate, you use multiple. If you're focusing on small files, mid-sized files, just want to get it from a single tape, so you don't want to cause big latencies, you use single tape. And this can be done with very small overheads, much less than 2-copy type system overheads, definitely substantially less than 3-copy, but with durabilities much higher than 11.9 durabilities. So you gain lower cost, higher durability, and higher performance. One of the key features is locally repairable characteristics. What that means is you have a tape, has a local problem, local ECC cannot correct, it's a bigger defect, bigger burst error, repeatable, then the per tape local erasure code system will be used to recover the data from that damaged tape, which means you don't need to get data from other tapes, copies to correct the error local to that tape. That it helps system I/O bandwidth tremendously. Tape errors. Now, establishing error parameter for tape and tape robotics can be a complex problem. Now, table here, basically we show error rates experienced by quantum over the years of our involvement with the tape systems, which goes back to decades. And these are not actual numbers, they're close to them, so they're approximate, as you can understand. And most people talk about 10 to the 19. I'm gonna leave that one off. I discussed that earlier. It really is a case for random small burst errors. So we can definitely correct that with more than 11 nines durability, and with LTO-9 more than 12 nines. This number was for LTO-8. However, most dominant errors such as edge, surface damage, pin drops, load failure, stop tapes, cut tapes, even lost tapes. Okay, as we can see from this table, these are less than 0.1%, which is about 3 nines, but it's not zero. So you need additional copies, additional tapes, erasure-coded tapes or copy tapes to correct for these. This two-dimensional erasure code focuses on this thing. Many of these errors can be recovered by the per tape dimension, whereas certain unrecoverable ones that you physically tape is damaged or lost, you rely on the second dimension. Overall, when you combine these two dimensions with overheads less than 2-copy system, you end up having substantially higher than 11 nines durability. How do you model durability with cold storage? Modeling cold archival storage systems can be a very difficult challenge. Current HDD-based systems rely on two-state available and failed Markov models, which may not be applicable for tape or other type of cold storage systems because HDD systems requires 24/7 data availability with any HDD. Tapes, they're stored offline. They're not on the drive unless you load them. When you load them, you run into these other real world problems that you have to deal with. So we found out in quantum with our research on data durability for cold storage applications that system needs a new state. So we call that the detected state, as it's shown in bubble 1, there with 3-copy basic Markov model with available and failed states, 2 states. And bubble 2 shows on the right-hand side, just below that, same 3-copy system, now modeled with a third dimension, which is called third state, which is called detected state. So basically now you get a much more complex system. Unlike today's two-state Markov models, there is a closed form equation. With the third state, when you apply this thing to the erasure codes, copies, geospread with robotics, you can't develop a closed form equation easily. So what we have done, instead, we have built a model as is shown in the block diagram on the left-hand side that physically computes, estimates mean time to data loss, mean time to data unavailability metrics for any system per tape, two-dimensional erasure-coded copy, geospread combinations with robotics, drives, and cartridges with all types of errors fed into the system. Two-dimensional concept is like this is a very simplified view. You got files A, B, C. You put them in individual tapes with local parities, file A parity, file B parity, file C parity. And then you go across, you develop a parity tape that goes parity of file A, B, C and parity of parities as shown here. So if you want to read any file, you just go get that tape. If you have a failure with that tape, you don't go get the other tapes. You just use that local parity to recover the file. Unless you have totally damaged that tape, lost the tape, then you go to the second other tapes to recover it. The other feature of the technology is the fact that we are doing interleaving. And we're just not, when we're doing across multi-tape erasure coding, we're making sure that things are not aligned the way we don't want them to. For instance, there could be some correlated problems such as tracking at BOT with your set of tape drives with the tapes that you loaded. In that case, if you're relying on the second dimension to recover and you got correlated errors, you may find yourself having to retry and everything, which affects your performance. So what we do is, rather than we pick code words all lined up at BOT of every tape, we interleave them such that they are at different locations on tape. This helps the durability 9 calculation because our systems now the errors are more randomized, just like the tape format. One simple example, which shows the power of two-dimensional erasure-coded application with locally repairable case. And this is a chart, a diagram with X's shows the errors. I got 7 tapes. Each tape has 5-2 erasure code, 2 parities, 3 data. And tapes have 2 second dimension, multi-tape dimension has 7-2 erasure code, 5 data tapes, 2 parity tapes. And I want to read file A from tape number 1. And when I try to read, it has 3 X's, 3 errors. So it's more than its local parity, definitely fails. So now I need the other tapes. The goal that we have is don't read the entire tape structure, just read what we want, only the sections we want, and do an optimum decoding process so we can calculate the file with many errors in a minimum time with minimum tape usage and minimum number of the sections that we read. And we use reorder read for this, definitely. I mean, that's one of the things we use. So now what we do is, first we decode rows 1 and 5, correct the errors. Then we decode columns 2, 4, 5, 6, and 7, decode the errors. We end up on the bottom right corner, 6 errors with X's. 3 on tape 1, 3 on tape 3. Now I do a row decode rows 2, 3, and 4, and I get the file. As a result, I do a row, column, row type iterative decoding to calculate my file when I have a massive number of errors where system can still recover the data. And let's see some example, a real world example. I got two cases here. The one on the left, I actually physically, both tapes are erasure coded, written, read, verified, and then damaged, and then reread. With standard method, without assuming there's an erasure code, it fails miserably. I mean, just like a hard, forget it. 20 minutes into the system, the drive just gives up. It says, I can't do it. But same drive, same media, we just software, just turn the switch on, let the per tape erasure code do his magic, and it just totally corrects for all these errors, repairs the whole tape, puts them into another tape without requiring any second copy. That's the magic of the system. So this brings it to the end of my presentation. And with that, I thank everyone for their attention. This is Turgay Gokar.